Please keep in mind that these questions cover key concepts in SQL Data Warehouse design and implementation, including schema design, data modeling, and data aggregation. 1. What is a star schema and how does it differ from a Snowflake schema? A star schema is a data warehouse schema that consists of a central fact table surrounded by dimension tables and preferred for simpler and more straightforward reporting and analysis needs. A Snowflake schema is a more normalized version of a star schema, where each dimension table is further divided into multiple related tables and suitable for more complex data models where data integrity and storage efficiency are priorities. Differences between star and Snowflake schemas. A. Complexity. Star schema is simpler and easier to understand. Snowflake schema is more complex due to normalized tables. B. Performance. Star schema generally offers better query performance due to fewer joins. Snowflake schema may have slower queries due to additional joins. C. Data redundancy. Star schema may have redundant data in dimension tables. Snowflake schema minimizes redundancy through normalization. D. Storage. Snowflake schema can be more efficient in storage usage compared to star schema. 2. What is the difference between a fact table and a dimension table? In a data warehousing context, fact tables and dimension tables are core components of star and Snowflake schemas, used to organize and structure data for analysis and reporting. A fact table is a central table in a star or Snowflake schema that contains the quantitative data, facts, for analysis. These facts are typically numerical values that can be aggregated and analyzed, such as sales amounts, quantities, and other metrics, whereas a dimension table contains descriptive attributes, dimensions, related to the facts in the fact table. These attributes provide context and are used for filtering, grouping, and labeling the data. Differences between fact table and dimension table. A. Purpose. Fact table stores quantitative data for analysis, whereas a dimension table stores descriptive attributes to provide context to the facts. B. Data type. Fact table contains numerical data, measurable, whereas a dimension table contains textual or descriptive data. C. Relationship. Fact table contains foreign keys that reference dimension tables, whereas a dimension table contains primary keys referenced by the fact table. D. Granularity. Fact table represents transactional or event-level data, whereas a dimension table represents descriptive data at different levels of detail. E. Use in queries. Fact table used to perform aggregations and calculations, whereas a dimension table used to filter, group, and label the data. 3. What is data aggregation and how is it used in a data warehouse? Data aggregation is the process of gathering and summarizing data from multiple sources to produce a dataset that provides a comprehensive view of specific metrics or key performance indicators, KPIs. In data aggregation, raw data is collected and then transformed into meaningful summaries, often through operations such as averaging, summing, or finding minimum and maximum values. This process is crucial in data warehousing and business intelligence to help organizations analyze large volumes of data efficiently and make informed decisions. How is data aggregation used in a data warehouse? In a data warehouse, data aggregation is used to streamline the process of querying and reporting. Here are some key uses and benefits. A. Improved query performance. Aggregating data reduces the amount of data that needs to be scanned during query execution, leading to faster query response times. For example, instead of querying millions of rows for daily sales data, aggregated data can be used to query monthly or yearly sales figures quickly. B. Data summarization. Aggregated data provides a summarized view of the underlying detailed data, making it easier to derive insights and identify trends. For instance, daily sales data can be aggregated into monthly and yearly sales summaries. C. Efficient storage. Aggregated data takes up less storage space compared to raw, detailed data. This helps in managing storage costs and optimizing data retrieval. D. Simplified analysis. Business analysts and decision makers can perform analysis more efficiently with aggregated data. For example, a sales manager can easily analyze monthly sales performance without having to dig through detailed transaction data. E. Pre-computed results. Data warehouses often pre-compute aggregated results and store them in summary tables. These pre-computed aggregations enable faster access to frequently used metrics, reducing the computational load on the data warehouse. Benefits of data aggregation. 1. Performance. Queries on the monthly or regional sales summary tables will be significantly faster than querying the detailed sales table. 2. Insights. Managers can quickly identify trends and make decisions based on aggregated monthly sales data or regional performance. 4. What is data partitioning and why is it used in a data warehouse? Data partitioning is the process of dividing a large dataset into smaller, more manageable pieces called partitions. Each partition can be processed and queried independently, which helps improve performance and manageability in data storage and retrieval. In the context of a data warehouse, partitioning is a crucial technique for optimizing query performance, enhancing scalability, and improving data management. Types of data partitioning in a data warehouse. A. Horizontal partitioning. Data is divided into rows, with each partition containing a subset of the rows. Common methods include range partitioning, based on values in a column, and list partitioning, based on discrete values. B. Vertical partitioning. Data is divided into columns, with each partition containing a subset of the columns. Useful when different queries access different subsets of columns. C. Hybrid partitioning. Combines both horizontal and vertical partitioning to optimize for specific query patterns and data distribution needs. Why is data partitioning used in a data warehouse? A. Improved query performance. By accessing only the relevant partitions, queries can execute more quickly, reducing the amount of data scanned and processed. Example: queries filtering on a date range can directly access the relevant date partitions instead of scanning the entire table. B. Enhanced scalability. Partitioning allows the data warehouse to scale more efficiently by distributing data across multiple storage locations or nodes. Example: large datasets can be distributed across multiple disks or nodes, enabling parallel processing and reducing bottlenecks. C. Efficient data management. Simplifies tasks such as data loading, backup, and archiving by allowing operations to be performed on individual partitions. Example: new data can be loaded into specific partitions without affecting the entire dataset, and old partitions can be archived or purged independently. D. Optimized storage. Different partitions can be stored on different types of storage media based on usage patterns, such as placing frequently accessed partitions on faster storage. Example: historical data can be stored on slower, cheaper storage, while recent data is kept on faster, more expensive storage. E. Data locality. Enhances data locality by keeping related data together, which can reduce disk I/O and improve cache performance. Example: partitioning by geographic region ensures that data relevant to a particular region is stored together, improving query efficiency for region-specific queries.
like, share and comment, and don't forget to subscribe our YouTube channel.